It very strongly departs from Einstein's theory, but it starts in the same place because I'm trying to explain the strange behavior of light.
He calls the Big Bang as fantasy of physics,
But it just so happens that because the speed of light is so fast, it doesn't make any difference.
All the individuals have their different bubble of velocity space. Is that true?
If you're in the same place at the same time as someone else, you see the same light, but I say no.
Issue. Like, why is the speed of light same for different observers, observing from different positions and different velocities?
The further back we go, the harder it is to see clearly, and the more you can use your imagination.
Yeah.
Anyone can just cheat on a test and look at the answers and say, yeah, I knew that. Yeah, I know. It really just, they don't want to call it motion, because if they call it motion, they would say special relativity is wrong.
Hello everyone, and today we have with us Geoffrey Stone. And we are going to discuss variety of topics, especially talking about the expertise of Geoffrey. We are going to talk a lot about special relativity and your book as well. So, hello Geoffrey, how are you?
So, good, thanks. It's great to be here.
Yeah.
So maybe I should just start off telling you a little bit about myself.
Yeah.
So my academic background, I didn't study physics. I did it in high school, but beyond that, I studied philosophy, psychology, economics. But I've always been thinking about physics and interested in it and learning about it. And just, it's not so much, I'm not interested in all of physics. It's really just the deep questions that I'm interested in and the strange, hard to understand aspects of physics. And I always found special relativity hard to understand, hard to believe, and also hard to understand.
Yeah.
And also a lot of quantum mechanics is understandably hard to understand. So I just, I spend more time thinking about these things than necessarily reading and writing, but that's because they're hard to think about.
You know what?
That's where
I
I'm coming
have
from.
one. What is my first question today?
No, what is it?
So my first question
Still
is,
going.
but where is the rainbow?
A rainbow is just an image on the back of your retina. It doesn't exist anywhere. It's everywhere and nowhere at the same time. Just like the speed of light is if you try to map out its location in velocity space, which you can do with everything else. You can map out the locations of planets and stars and people and everything in velocity space. But if you try to do it with light, it doesn't go anywhere. Or it does, but the location changes depending on the location of the observer, which doesn't really make sense.
Okay, so for my viewers, I'd like to tell that But Where is the Rainbow is the book by our guest, and it's a wonderful book with some very important questions that is needed to be asked to this modern science, and try to fill the loopholes and blanks that are existing in the modern physics. So when I ask you about your book in a very summarized way, if someone asks you what is your book about, and the second question connected to it is it well aligned with Einstein's theory or it departs somewhere? Please explain.
It very strongly departs from Einstein's theory, but it starts in the same place because I'm trying to explain the strange behavior of light. So basically what I'm saying is light is weird, but in order to explain why light is weird, you don't need to say that time and space are also weird. And you don't need to say there's a thing called space-time. We can have the same old 19th century ideas and intuitive notions of what space and time really are. We can keep them, and we can explain why light is so weird. So it's
Okay.
more, in
So,
that way, it's more parsimonious because it doesn't require as much that we change as much to accommodate the strange behavior of light.
yeah, after 110 years of Einstein's theory, okay, we are still stuck in a paradigm where we have a lot of questions unanswered, a lot of problems unsolved. Like, let's take an example of light. When we talk about Einstein's special relativity that came in 1905, it has a postulate where it talks about the invariance of speed of light, which sounds kind of weird to a lot of readers and a lot of students. So, what is your take when it comes to Einstein's special relativity and using that to explain the whole universe?
So the way I look at it is I think about velocity as a space. So it's a vector space. So you can map everything out in this vector space. And if you do that, it changes the way you look at the speed of light. Because if you think of it spatially, what would you say if an object was always the same distance away from you, no matter where you were? Right? That's not how objects are. They change their distance. When you move around in space, the objects appear to move around, and we know that
Yeah.
how far away something. There's a difference between where something is in space and where it is relative to you. But with light, there is no difference. The speed of light is the speed of light relative to you. It never changes, and that's kind of weird, right? So I use the idea of space as a model for how to think about it, and to realize that it can't be real. It can't really be. It can't change depending on where you are in velocity space. So I say you have a location in velocity space, and your location in velocity space is your frame of reference, your inertial frame of reference.
Okay. Does this
And also,
is
it is your velocity.
please,
So you could
please?
also
Yeah.
say a distance between 2 points in velocity space is a speed. All right, speed. So we can go back to
Okay.
Galileo and Newton, where they had a revolutionary idea that all speed is relative, all motion is relative. And that's true, and it makes sense. But what that really means is that in order to have a speed, you need 2 points. You can't just have one, right? You don't really have a speed because you need to connect that to some other point. And once you have
Yeah.
2 points in
Relative.
velocity space, then you have a speed that connects, and the direction in which they're related is there as well. So the speed is
Okay.
the
So,
distance, the direction is the direction.
is it like following the traces of we can say velocity space given by Galileo?
Yeah, it stays true to Galileo and Newton, and it departs
Okay.
from Einstein, and it simply accounts. So I'm using quantum mechanics as well, in a sense. It's a little bit awkward in some ways, but the idea is just like an object can be in multiple places at once or have multiple states at once, light can have multiple speeds at once. And just as actually this explains why light moves in multiple directions at once, because it expands outwards like this.
Okay.
Nothing else really moves. I mean, waves do, sound waves do, but those aren't objects. But none of the objects move in multiple directions at once. But light does, and we say it's an object because it's a photon, it's a particle, right?
Yeah, it's a particle. Yeah.
So it can move. The particle moves in multiple directions at once. But I say it also moves in multiple speeds at once. So that's speed, direction. Those are the 2 parts of velocity. So it's a super velocity. That's why I call it super velocity and selection theory of light.
Okay.
It begins as a super velocity, and the observer selects the velocity they see. So just as So when the light's expanding in multiple directions, you don't see all of it. You only see the light that actually hit your pupil. But you know the
Yeah,
rest is there.
exactly.
And if you move,
Yeah.
you'll see a different part of it. It's the same thing
Yeah.
as we move in velocity space. As we accelerate, we see different parts of the superwave. It's the same light in a sense, but it's also different.
Yeah, we are going to talk more about the velocity space, but before getting deeper into that, let's first talk about Einstein's relativity and the point that dissatisfied you, that created a kind of discontentment in you, so that you develop
Okay.
a new concept of seeing the same thing. So, what were the cracks or the loopholes that haunted you?
There's a few things that I eventually identified. Originally, it took a while for me to put my theory together, and it sort of all came together near the end. But I was thinking that maybe the speed of light was infinite because there are certain ways in which you can look at it and it seems infinite.
Yeah.
And yet it's also very obviously finite. And so how do we make sense of that? The way we measure motion, the way we measure time is usually we use an oscillation
Time. Yeah.
or a rotation, right? That's the
Yeah.
way that makes sense. We don't use inertial motion to measure time, ever. Only in Einstein's light clock thought experiment does he just use inertial motion in the sense that you have the light moving at a constant speed in a particular direction,
Yeah.
right? So that's not how we measure time ever, because we know that that would make it dependent on your frame of reference. But because the speed of light is constant no matter what your frame of reference is, he thought, well, that you can do it in that special case. But that creates problems, right? Because now
Yeah.
it's not, what you're not measuring a true distance. I say there's a thing called true distance. There is a such thing as how big Earth is. It's not a matter of perspective.
Yeah.
So, but what he's using is what I call frame dependent displacement, which is how far a moving object moves over a certain period of time. And that
Yeah.
does depend on your frame of reference. But it just so happens that because the speed of light is so fast, it doesn't make any difference unless you're considering objects that move very, very fast.
Okay.
So I guess what I'm trying to say is I distinguish between a frame-dependent displacement and a true distance. They're not the same thing. A true distance is real. A frame-dependent displacement just depends on doing some calculations with, time, space, velocity to come up with a number, but it depends on your frame of reference. It's totally different.
I'd heard
So the light clock, the
from
reason, so
it-
yeah.
Yeah, I heard from you that talking about the true distance and the kind of observer dependent distance, you give an analogy which tells that if you have $10 in a pocket, then that's an objective truth that yes, you have $10. But when we talk about other perspectives, then people might think this is 10 candies. Someone thinks that it is a ride to some place. So the value differs with perspective, but its objective value or the real value, it remains constant. How is this related? Can you connect this?
So I use in my book an example of if let's say you have three different people with different amounts of money in their pocket,
Okay.
and you say somebody has $3 more than you, but they all have different amounts of money, and you say, well, this person has $3 more than this person and that person and that person. It's exactly $3. That doesn't make sense.
Yeah.
Now you could say, well, the value of money is always $3. They all agree that this person has $3 more, but that they don't really agree. They're just agreeing with a partial statement. It's not a full, complete thought. They're saying this
Yeah.
person has $3 more, and that's a fact.
More.
$3 more than who? You just have to ask the question. More than who? The
Okay.
speed of light is relative to what? Faster than what? There's another analogy I like to use. It's Why can't you go
Yeah.
faster than the speed of light?
Yeah.
Well, you
I'd
can't
love
run
to.
faster than your shadow
I'd love to hear that. Okay. Why can't we travel faster than speed of light? Yeah. Let's dive in.
because every time you change your location in velocity space, so does the light that you can see. It's like a bubble. It's
Uh,
basically a bubble in velocity space
okay. Does
with a
this
radius.
mean? Yeah. Does this mean that like all the individuals have their different bubble of velocity space? Is that true? Okay. Yeah, please
Yes, although
continue.
for all practical purposes, because we're all on the planet Earth, so we all have the same velocity bubble because we're all in the same location basically in velocity space.
Okay.
So we all see the same light. But if you have a thought experiment where someone's in a spaceship or traveling very fast, or anytime you're moving really fast relative to someone else, then you do have different bubbles. Uh, and so the bubble is just the light you can see, which is not really all the light.
Okay.
Just like two people in different
It's
places see different light. So,
yeah.
prior, and Einstein would have thought this, and everyone would have thought this. If you're in the same place at the same time as someone else, you see the same light. But I say no. You have to also be in the same place in velocity space, which is normally the case. Because if you're just, stuck together in the same place, you're also in the same spot
Yeah.
in velocity space. But if you happen to be moving really fast in different directions and momentarily you're at the same spot, you're in different place in velocity space, but you're in the same place in space and time. In that case, you'll see
Okay.
different light.
So I think that there's a problem in Einstein's relativity that occurs when we try to talk about the speed of light. How can it be different for different observers, right? This is a kind of problem, and it's non-intuitive when we try to get deep into it. So I feel like this your concept is trying to solve this issue. Like, why is the speed of light same for different observers from different positions and different velocities? Am I going aligned with your thought?
Right.
Yeah.
Yes,
Okay.
because I don't assume that there is a speed of light. I assume that we see what looks like a speed of light, but that's not the whole story. Just as if,
Okay.
in a double slit experiment, what you see, the photon lands in a certain spot, but that's not the whole wave function, right?
Okay.
The wave went in multiple directions, but you don't see all that. You just see the spot where it ended up.
Yeah.
However, it seems to the selection process happens randomly, which just means we can't predict it. But in the case of the speed of light, we can predict what we'll see, assuming that we know where the observer will be in velocity space, because we know it has to be a certain distance away. So that's the only real difference.
So if we
So I
go
say
through this
so.
path, if we go through this path, then is it possible that we could calculate the one-way speed of light somehow going through this concept, or is there some possibilities out there?
That's a very good question. I really haven't thought about that, but I think yes, that would imply obviously that there is a one-way speed of light. If
Yeah,
well,
there should be one,
not a
right?
one-way speed of light, because it's not the light; it's the light you see, and that
Ah,
changes,
okay.
right? So if you happen to change, so the light, if it's bouncing between two mirrors, it's changing its speed, its direction as it bounces.
Yeah,
You could have changed your
yeah.
speed and direction in that amount of time, and you're not seeing all the light anyway. You're just seeing part of it. But the part you see, yes, and that kind of leads me to
Okay.
a prediction that my theory makes, because the Earth changes its speed and direction, and that gives us
Yeah,
parallax, right? Because we're moving in space, so we can see the stars
yeah,
wiggle, and
yeah,
but we're also moving in velocity space. As we orbit, we're changing our speed and direction.
yeah.
It kind of depends. You could say we're in inertial motion. I'm not sure. we could go that route too, but I'd say we are changing our speed and our direction. We are really accelerating.
Okay.
So we're changing our
So
location in velocity space.
when our Earth is orbiting around the sun, okay, so it's kind of changing its velocity every moment of time, right? It's kind of changing its
Mhm.
velocity. There's some kind of acceleration out there. So during orbiting around a heavenly body, is there what is happening in the velocity space? What is happening? Like, are things moving in the velocity space, or what's happening? Can you like clarify this?
Yeah.
Yeah.
So velocity is your position. Your velocity is your position in
Okay.
velocity space, but your acceleration is your velocity in velocity space. Everything
Ah,
is moved up by one derivative, right? So
yeah.
you can you can map out. So we actually have an orbit in velocity space. It's roughly circular,
Oh,
and
okay. So
it's
it
tilted
means
90 degrees away from our
uh,
orbit in space. And the planets
okay.
that are further away from the sun have smaller orbits in velocity space, and the Mercury has the
Smaller
largest
orbits.
orbit in velocity space.
Okay, can
Right.
you
So if you
elaborate this?
wanted to
It's
see,
going interesting. Yeah.
well, because Mercury moves so fast, it's accelerating faster. It's being pulled more strongly by the sun.
Okay.
It has that gives it a larger um, orbit in velocity space
A kind
because
of
the
larger
distance between
displacements
the
in
sun.
velocity. Is it like larger
So the
displacement in
side,
velocity?
yeah, there's a bigger difference between the speed of Mercury and the sun than there is between the speed of Earth and the sun. And the
Yeah.
speed of, say, Neptune is a lot closer to the sun because it's basically getting pulled along with the
Yeah.
sun, right? So it's usually in about the same
Hmm.
location in velocity space. If you look at the galaxy in velocity space, all the stars, it forms like a ring, which is what shocked everyone. This is why we came up with the theory of dark matter, right? Because they were expecting to see what looks like the solar system, where planets that are further away orbit slower, significantly.
Yeah.
And they found no, that the distance from the center of the galaxy doesn't matter too much. They're all going at about the same speed.
Yeah. Yeah.
And so in velocity space, when you map that out, it looks like a ring. So that's, I don't know,
Okay.
just an interesting thing.
So
Also, at the
does
large
this
scale,
concept is this concept kind of neglecting the existence of dark matter, or what is it?
it doesn't really have much to do with dark matter, I think. But
Oh,
I personally have never been a fan of the theory of dark matter for other reasons. I
okay,
just
okay.
think it just seems like a post hoc, ad hoc kind of fudge
Same here.
factor. So
I feel like
I mean,
there
we
was a,
never would have predicted it. So let's not pretend we understand it because we wouldn't have predicted it. You know what I mean?
yeah,
So
yeah. It's already been hundreds of years, and we are still far away from its investigation, or even like getting to a conclusion that it exists or not. Right? We still don't know.
I was gonna say, yeah. Now with the new telescope observations from the big Hubble 2.0,
Yeah.
apparently a lot of ideas about dark energy. Well, I don't know about dark matter, but certainly our observations of distant galaxies are shocking and surprising in many ways. And
Yeah.
you know what? Honestly, I never really believed in the Big Bang theory. So
Oh, really?
again,
We have.
ever since we discovered dark energy, I
Yeah.
figured, well, we don't have as much reason to believe in it because we have another explanation now. Now we just know,
Yeah.
well, the universe is accelerating in its expansion, and that's why it's expanding. Something's pushing
Ha-
everything apart, and we don't even know what that
have you
is.
have you heard Penrose talking about this? He calls the Big Bang as
No.
fantasy of physics. You know, he calls it a fantasy.
Further the further back we go, the harder it is to see clearly, and the more you can use your
Yeah.
imagination. And it's okay
Yeah,
to use,
yeah,
it's
yeah,
okay to use your
exactly.
imagination. Just have to, as long as you
Yeah,
acknowledge it.
but don't try to like keep on top of everyone's head that this is true, right? So talking about
Yeah,
scientists,
that's when it becomes a religion. It's okay.
who inspired you to get into physics, or what was the thing, the most important thing that helped you begin in your journey into physics?
Uh, I owe a lot of debt to the show that I've watched. Well, they didn't inspire me to get into physics, but I've seen a lot of episodes of PBS Spacetime.
Okay.
I don't know if you're familiar with this show.
Yeah,
And
I
while I'm
am.
at
I
it,
am.
I should give a shout out to a YouTuber named Dialect Philosophy. They
Okay.
do a lot of good stuff
Cheers.
pertaining to special relativity and general relativity, and we agree on basically everything. I mean, they point out a lot of the flaws with
Yeah.
special relativity and general relativity, just conceptual
So
stuff, just like things that don't really make sense.
there's no one particular scientist that have kind of led you as the
Oh,
engine of the train. No.
I like Karl Popper. He was my favorite philosopher.
Okay.
He's the one who came up with the idea that a theory must be falsifiable.
Yeah.
It's sort of
Exactly.
like when you place a bet, right? You make a prediction
Yeah.
before you know anything, not after the fact. Of course,
Yeah.
anyone can just cheat on a test and look at the answers and say, "Yeah, I knew that." Yeah, yeah, I know.
Yeah.
Anyone
Yeah.
can
Yeah.
make it fit. You can make the data
Yeah.
fit with an infinite number of theories. So that's not
Yeah.
where the work of science should be. I mean, it's fun, but what you
Yeah.
should have is a well thought out, clear theory that makes predictions, and then most of
It
those
should
theories
be
should be
falsifiable.
killed by observation. Yeah.
Yeah. So yeah, once we get along with a theory that we call as the ultimate theory, or it's not falsifiable, it's the greatest one, then it turns to a religion from science, because there is a very small difference
Yeah.
between religion and science. And science tells that we need evidence, right? We need evidence, and we are not going to believe anything. We must know it or not know it, right?
Yeah. Unfortunately, evidence doesn't always give us everything we want, because you can always find different ways to interpret the evidence and
Yeah.
fit it to
Yeah.
some theory or describe it in different ways. And there's, a lot of it is a battle over language, what language to use. Or maybe mathematics is our language. Maybe we should just speak in mathematics. Maybe there's a
Exactly.
lot of people who think that. I don't think that. I think that mathematics is a very useful tool. It's very helpful, but we don't want to be too dependent on it, because we're not naturally equipped to think in mathematics. We have the languages that
Exactly.
we evolved, that our brain evolved to use, are natural
Yeah.
languages. And mathematics is very restricted.
Yeah.
There's so much you can't say in mathematics.
Yeah. Yeah. Yeah.
In some ways that's good, but in a lot of ways that really
Yeah,
uh, it makes it easy to make mistakes.
we are very familiar with the story that when Newton was trying to come up with his theories with the Principia, and he thought that something was lacking in the entire mathematics, and he came up with calculus, right? So there might be
Mm.
things that to explain those things, some maths are yet to be like invented or discovered, right?
What
So
also part
yeah.
of the part of yeah part of why we have a theory is to make something understandable. So a computer might use mathematics and understand something perfectly well, but it can't explain to us what it's doing and what it knows, right? So it
Yeah.
still needs to be able to speak in some sort of language, some other language, to really get that understanding across. So even though you can understand things mathematically uh, well enough to make predictions, uh, you still need that element of making a connection to natural language at some point, so
Yeah,
that
George.
a person can understand it.
Absolutely true. So we are heading toward a very wonderful conversation, and we'll be back after this short commercial break. So welcome back. Let's get back to your book.
I'm working on a new book now, and I'm writing a section about time, and so I've been thinking about time a lot, and I'm sure you've been thinking about time a lot too.
Yeah,
And I have a
a
question for
lot.
you. So let's say you
Please.
have
Uh,
like seven. Let's say you have a whole bunch of clocks with you. They all work according to different principles. So one has a pendulum, another has a balance wheel,
oh,
another has, let's say you have a light clock, an
as-
atomic clock, and a whole bunch of different
okay.
clocks, okay? And I just
Okay.
magically snapped my fingers and I made time speed up. Now time is going
Yeah.
twice as fast. What would happen? How
So
would you
you
know?
speeded up the time.
Yeah.
So we
So
I
then,
have to
so if that
first of
happens,
all, yeah, please. I'll ask
also
you.
I'll answer my own question, but uh, so what Einstein says and what I would say is that nothing would happen
Yeah.
because all the clocks would speed up and your brain would speed up and you wouldn't notice anything, right? So in that sense,
Yeah.
time is kind of meaningless. You can't measure it, right? What else could happen is
Yeah.
I could do something that slows down one of the clocks because they all work according to different principles. So maybe the one that has a pendulum, if I increase the gravity, the pendulum clock will start to swing faster. So then time goes faster. But then the atomic clock would start to tick slower because atomic clocks do tick slower under stronger gravity. And now the problem is we, in physics, artificially has created this monopoly on time by making the atomic clock the standard, right? So we define time based on what the atomic clock tells us. Really, it should be more general. It should.
How we calculate time is how many times is the cesium atom getting excited and getting back to its orbit in 1 second, right? That is how we have standardized the time. This is what time is. We have defined it. So yeah, what is your take?
Well, the original standard, which worked pretty well, was we used the orbit of the Earth and the Sun, and it's not absolutely precise, but then again, nothing is. But when we changed that, see, we could all have a common reference for a time point when we had that, right? So we could definitely say what time it is. But if we say it's whatever a clock says, and we can have clocks, we can move them to different places, and they can go different speeds, and they can have different frequencies at which they tick. Now we can say time is all of these clocks, and we have to arbitrarily pick one, or we can say there's time dilation and all that stuff. But if we go by the original standard, we can't really say that because time is global and universal. So it's really up to us what we want to say. Now, it is arbitrary to just pick the Earth and the Sun as a basis for time, but it's also arbitrary to pick an atom.
Yeah.
So
we might have talked about the motion of one galaxy that is like moving in certain speed. We could have taken that as the reference of time as well, right? But that
I
is
think
out of reach.
that'd be way better. That's way better to expand rather than shrink. We've shrunk it down to an atom. It's better to think bigger and look at, like, say, neutron stars or other solar systems. We can use that to calibrate our system. We can keep the seconds and the days and the hours and all that, but to give us more stability, we should expand outwards instead of going to a single atom, which apparently can be manipulated by gravity or acceleration. So, I say if you pluck, let's say we make a guitar string as the definition of time when we pluck it. Okay, so it vibrates a certain rate, and we use that. We make a clock out of it. All right, now I turn up the knob. Did I just speed time up? I don't think so.
So
I
so
just
does
turn the
this
knob.
mean that you so this means that you want a clock that we are not capable of making impact or like making some changes in, right? Like we can't change the
Yeah.
velocity of a galaxy, right? We can't change the planetary motion. So things which are not under our control or under our control in a sense that we can influence the clock. If it goes bigger, then our influence gets smaller. Is that what you mean?
I'm also trying. That's part of it. It's also just trying to distill what is time that's and what is another variable, right? So uh, we could say gravity changes the flow of time, but what if it's just the thing that's measuring the time that's being affected by time and gravity? So we're sort of
Yeah,
conflating the two. Right. So it's like if you want to measure
yeah.
inflation, like I have an economics background, a lot of people are saying there's lots of inflation, but I say that's not really true because if you use the standard of a basket of goods to measure inflation, then yeah, it looks like we have inflation because all the stuff in your basket is more expensive. But if you were to use, say, the exchange rate or purchasing power parity or just the money supply, it doesn't look like we have inflation. Really, it looks like certain goods are harder to obtain and so they're more valuable and so they're costlier, right? But we're calling it inflation because that's how we measure it, even though conceptually there's lots of
Yeah.
ways to measure it. So it's always good to think about all the different ways we can measure the same thing to make sure we're really measuring that thing. And if we restrict and narrow our definition to that's just what this atom's doing, that's time, or to measure space, right? Or let's say the meter is defined as the amount of space covered by light in a certain amount of time,
Yeah.
right? So
1 by C.
that's now how we
Yeah.
define it.
Yeah.
That I don't think that was a good idea because
Okay.
now it's
So
like
something
special.
that can be influenced, if something is under our control, then it can be distorted, right? And when it
Mhm.
comes to time, even I feel that it's just a reference, right? It is just a way to make our daily life easier. Like we can't tell someone that come to meet me when the sun is exactly on top of her head or sun is in this angle. We can't tell that. So we developed a way in which we can tell in numbers. Like, okay, come to meet me on 3, 4, 5, 6, 7, 8, right? So we have we have divided or quantized time in the second, and we are trying to give a reference. Or do you think that time is really a thing like a dimension? And if not, how is it different? How is it different from the space?
I think that time causes our concepts to evolve. So we start out with concepts that are practical, like, yeah, simultaneity is something that we use to help to meet, so we can meet. I want to synchronize my clock with yours so we can meet at the same place at the same time. Otherwise, if we meet at at the wrong place or the wrong time, we're not going to meet. So it's very practical. The thing is, once Einstein and others have kind of gotten us away from the practical and more into the abstract. So we're expanding our concepts now. So we're deciding we're way out of our home territory now. How are we going to change our concepts? And we'll have to make decisions, like seemingly arbitrary decisions, about how our concepts are going to evolve to incorporate strange scenarios that would never happen. So I would never set up a meeting with an alien in a distant galaxy. So that's why I don't have a concept of simultaneity that incorporates a huge expanse of the universe. I just have a concept of simultaneity that's for earthly purposes. But if we're going to expand our concept of simultaneity, we need to. I'd say we should try and stay true to our original idea. That's all. So, and the funny thing about simultaneity, well, anyway, it gets into complicated things like, well, Einstein's idea of simultaneity is actually based on the speed of light, which doesn't depend on your frame of reference somehow. But if it did, he would have come up with a different idea. I actually believe that you can have a meaningful simultaneity for very distant objects, which doesn't depend on your frame of reference.
Okay.
Because
Can
because
it
of
be
how I
like,
look at space time and
so is it like we can set up a clock somewhere in the sky by looking at some bright star that is far away from us and very out of control when it comes to our influence? Can
we
it be a new
we could
clock?
call
New way of, yeah.
we could talk to an alien civilization that has advanced science like us and that we speak the same language somehow, and we could say to them, well, it would take a very long time for our message to get to them, but if we could, we could say, hey, why don't we meet when that planet intersects with that planet, or something like that, and we both understand what that means, and maybe we'd calculate it in different ways, but we both get the same conclusion, and we could reach the same place, but we wouldn't have to actually synchronize clocks.
Yeah. Yeah.
But I think even if we
exactly.
did have to, we still could. We probably could, because I think time works the same way. I don't actually think that a clock slows down when it.
If we are in contact somehow with an alien civilization having the same way of communication, and if we want to meet them, we will tell them that let's meet when this planet intersects this planet, or eclipse of this planet or this stars. We can do that, right? You talked about far future, right? It's we can imagine it in future, okay? But if you are aware about, have you read any Hindu books, like any books related to Hinduism, or no? So
I haven't. No.
it might surprise you a bit, because all the like Hindu scriptures, when it comes to Veda, and there are branches called Puranas, where time were explained exactly what the way that you explained right now. When you ask some Hindu, when was Rama born, right? Rama is a god of a deity of Hinduism, and when you check the scripture, when was Rama born, then you'll find that there's no time AC, AD, BC, or something like that. There are interpretations like, when Rama was born, this planet and this star system were behaving in this way, and they were aligned in this way. Okay, there are a lot of those kind of explanations. So I think
It's very concrete.
5,000 years, yeah, 5,000 years ago, they had like very rich understanding of astronomy. We must say that, right?
I'm sure they did. Yeah. I don't know too much about ancient civilizations, but I suspect that a lot of what we knew has been lost, and
Yeah.
I suspect that humanity has had this potential for a very long time, and perhaps for our own benefit, or we've been sort of constrained because we don't want to open that Pandora's box. But
Yeah.
I don't know. I don't really know. You know what I mean? Because
Even I sometimes.
we could have had a civilization.
Yeah,
We could
please.
have had huge civilization perhaps 50,000 years ago. We were pretty much the
Yeah.
same species. Why now? Probably someone opened Pandora's box. That's what it looks like. Anyway.
Or it might be that someone closed down the Pandora's box.
Yeah, I think so.
might
And a lot
happen,
of
right?
religions sort of preach about, maintaining stability, and there's a lot of things that you're not
Yeah.
supposed to do. And a lot of what we're doing now is things that we're not supposed to do. We're messing with nature, we're messing with
Yeah, like
the technology is is good and bad. But it's definitely throwing things out of
Yeah.
balance.
today we interpret technology as how badly we can mesh up the environment, how worse can we make this earth, right? That is technology these days. And I talked about the Hindu religion and Hindu scriptures. I would like to mention one more thing. There's a scripture called Surya Siddhanta. It is also one of the Hindu scriptures. It explains about the astronomy and a lot of astrophysics in it. And it has predictions like distance of Earth from the sun's diameter, and about the planets of Jupiter, and a lot of other things that we came to know recently. And it's not just like a guess or something. The things are mathematical. Okay, when you convert the units into the units that we are used to now, it gives a surprise that how was this possible 4 or 5,000 years ago, when we got telescope just after Galileo, right? So even I feel like,
I wonder how they did that.
Yeah, I do. Don't you?
Well, it's in like in mathematics, you're always expected to show your work, right? But you don't have to.
Yeah.
You just have to come up with the right answer.
Yeah.
You also have an idea about yeah. So.
Yeah.
Well, what else? What have I not said? There's a lot. I think I've given you the basics. So I also to draw a distinction between manifest light and latent light. So Einstein didn't draw any distinction. So he's asking. So it makes sense to assume that if you send a beam of light off a mirror and bounce it back, you calculate the time. That's the time it took for the light to go. What my theory says is that's not all the light. So that's the manifest light. There's also latent light, which went other speeds. But it won't interact with you because you're in a certain place in velocity space. So the rest of it, you can't see. But it's still there. And I just call it latent.
Latent light and manifested light, right? Getting to our concept, like the concept that we have been working on, it's also named as, it's famously called ancient theory of everything when it comes to the coverage in this part of the world. So we are working on the absolute theory of the universe, kind of. Not when it comes to Einstein's relativity, everything is relative, right? Everything is relative, and we are working based on some observations and evidences that point toward the direction that our universe might not be as isotropic and as homogeneous that we are taught, that we believe, because we have evidences like axis of evil, the cold spot, and there are a lot of things that indicates the anisotropy, and one of them is we not being confirmed about the one-way speed of light till date is also a big question in our head, and we work with 4 dimensions of space in such a way that the 3 dimensions that we are used to is a part of the universe, and there is a 4th spatial dimension.
I heard you say that there's a 4th special dimension.
Yeah.
Like I get 3 dimensions, and I get how maybe time could be a 4th dimension.
Yeah.
But what do you mean by a 4th spatial dimension?
It's very much like a dimension that a 2-dimensional universe, like when we talk about 2-dimensional universe, a flat universe, height will be a dimension that is not accessible to that dimension. Okay, in a similar way, we are living in a 3-dimensional universe in such a way that we perceive 3 dimensions, but everything that we are watching around us, they are the shadows of the 4-dimensional entity. And when we postulate one thing, that is, if all the 4-dimensional entities are traveling at the speed of light, all the 4-dimensional entities are traversing through our 3-dimensional space in the speed of light, then when we go to the maths, we get the exact derivation of Lorentz factor. We get the Lorentz factor from this concept. And how it is different from our current understanding of physics is that it talks about the absolute theory of the light or anything. Like our universe must be special at some point in space, and it's not completely isotropic and not 100% homogeneous, as the recent evidence suggests as well. We might need a lot of time. Yeah. Yeah, please.
One idea that I've always toyed with, one way of explaining the original experiment that led to Einstein's theory of special theory of relativity.
Yeah.
What was it called
Yeah.
again? Michelson-Morley. One way of interpreting that would be to suggest that Earth is special
Yes,
in the
man.
universe, and that Earth is stationary. Now, no one would have thought Earth is stationary.
Yeah.
So they had to come up with
Exactly.
special relativity. But that is actually, it's more of an intuitive explanation. Which was shocking, of course.
That's
at the
what
time.
we are into.
No way, Earth is not stationary. Oh, really? Okay.
Yeah. See,
It's a
you
perfectly
you
acceptable
perfectly aligned with.
interpretation.
Yeah. So
I'm not
okay,
saying it's
let's get
right.
back
I'm just
to-
saying it's perfectly acceptable.
Yeah. So when we talk about Michelson-Morley experiment, let's get a little bit of detail of that experiment. Okay, Michelson and Morley. There's a time when Albert Michelson even gave a statement that our modern physics is almost to an end. We have nothing more to discover. These kind of statements. And in the same year, Michelson and Morley they planned an experiment using a device, an instrument called interferometer, and they were trying to detect ether. I know you know it very well.
Mm-hmm.
I'm trying to get it for the viewers. So
Yeah.
the experiment was basically to find out the speed of ether. Like there's a ether. If there's ether and this is moving, there might be a wind. Okay, there might be a wind in some direction because Earth is not stationary; it's moving. It's continuously moving. And that experiment gave null result. It means it showed that ether is not in movement with Earth. And that was the time when we drew two conclusions. Okay, one was the whole ether thing is crap, it's useless, just avoid it. And two, the second option or the second conclusion was that ether might be existing in such a way that it always stays at rest with the frame of Earth. And
Yeah.
people directly jumped to
I agree.
Einstein's interpretation just because they were scared, because the whole physics was broken down. People were looking for some alternatives, and they found Einstein with a concept called special relativity, which is still non-intuitive after 110 years of explanation, right? So I think this is the time when we need to open the box of Pandora and think that there are chances that Earth itself can hold a special position in this universe, right? Because we have an observation that tells that when all the galaxies around, like far away, were all observed with their redshifts and their speed at which they are traveling, the distance, then scientists found that all the galaxies were positioned in quantized concentric pattern. Okay, so if we consider Earth as the center, then we find all the galaxies in a concentric way, a sphere, a gap, a sphere, a gap, a sphere, in that way. So this also indicates that, are we at the center of some shell? And these are the questions, and
Are you
there are a
bringing
lot
back
of other things as well.
Epicycles? Are you suggesting we bring back epicycles?
No. See, I feel like epicycles is a kind of obsolete concept, I tell, because when it comes to gravity, right? When it comes to gravity, okay, gravity is not going to rule everything in this universe. It's just one aspect, right? And when we talk about gravity, Earth is revolving around the sun. That's perfect. And just like Einstein's relativity tells, there is nothing special about some body's motion, right? So if Earth is revolving around the sun, we can see it from Earth's perspective, that there is a motion as an impact or as the consequence of gravity, which doesn't keep Earth in the center of the system. But the other aspect, when we talk about the ether, the time dilation things, the beginning of the universe, the existence of galaxies around our Earth, there are a lot of things that indicate that Earth can be holding a very special position in this universe.
So here's my take on ether, because
Please.
I've always thought about this, interpretation of the the original experiment, but my theory doesn't say that. My theory says you have empty space, and somehow light travels through it. But the thing that makes the medium, if we want to call it that, the medium that light travels through, special, is that it doesn't have a location in velocity space because it's empty. Like it's an empty. So what's the location of nothing? What's everywhere, right? So the ether is everywhere in velocity space. So a planet has a spot in velocity space, but the ether is everywhere. So any message or any wave that travels through the ether or the empty space, whatever you want to call it, has no location in velocity space. It's everywhere.
Okay.
So it's kind of like a blank.
Nice take.
It's a fill in the blank. It's a fill in the blank wherever you need it to be.
So, I heard you saying somewhere that putting up a question in one of your video. Mm-hmm. You told that if light is traveling, if a photon is traveling at the speed of light away from us, then what's our speed? Right? Well, did I put it correct?
Yes. Yeah, that's a good question, eh? I mean, if the funny thing is, special relativity has all these mathematical conventions. So when you add one speed to another, you don't get, x plus x. You get something that has to equal out to less than the speed of light. And there's an infinite number of ways you can accomplish that with mathematics. The reason we chose what we chose is totally arbitrary, just because it looks good and it works, basically. But we have to throw out our old concepts of, adding speeds together to accommodate special relativity. And just to accommodate special relativity, we have to say that these distant galaxies we see are not moving away from us at faster than the speed of light, even though it looks like they are. Instead, we say space is expanding, and they're not moving through space. Yeah. They're sort of stationary in space, but the space itself is moving relative to space. Yeah. So that it's sort of like cutting corners or a loophole, you could say. But it really just, they don't want to call it motion, because if they call it motion, they would say special relativity is wrong.
Exactly.
Yeah, it's pretty obvious. Yeah, it's sophistry.
So we are running out of the scheduled time, and I don't want to end this conversation. So I'd like to announce something, that it is going very good, and we are soon going to record the part 2 and continue this conversation with a lot of more topics, because when we talked about the velocity space, I wanted to talk about the Heisenberg uncertainty principle, right? Because it talks about the velocity, right, and position, right? And as per your concept, you have different frames for these two things, right? Velocity and position.
Yeah. So
because position is in our three-dimensional space, while velocity occurs in the velocity space.
Yeah, so the more defined something is in velocity space, the less defined it is in space, and vice versa. That's sort of what Heisenberg says. And Newton says you're stuck in your location in velocity space. Everything maintains that position in velocity space unless a force acts on you. That's all.
But he said it in a very simple way, that everything continues to be in rest or in uniform motion until any force is applied on it, right? So
Yeah, but
thank you
another
so
way to
much,
say that would be that
Geoffrey.
okay.
Oh,
Thanks for having me.
we actually have a lot more to discuss, but thank you for your time, and thank you for your words, which are going to impact a lot of youths who are watching this out from different part of the globe. And let's hope that your theory, your concept, your book, and you yourself inspire more and more and more youth throughout the world. Yeah, please, thank you so much.
Okay. See you later.
पानी परिरहेको गरम गुरुङ रातैभरि मलाई के को चिन्ता म त थिएँ तिमीसँग गुड भाइब्स अनि मग मग स्मेल पनि फिल भइरहेको थियो मलाई मायाको तरङ्ग